Now, we're going to do both these coils here. This is the other side of it, right? So for your impedance, you have three things. You have, normally when you're looking at the graph, your resistance is this way, and your capacitance is going to be down. Your capacitive reactance is going to be down, and your inductive reactance is going to be up. Now, when you divide them out and you're trying to figure out your current, that makes your current lagging down here for an inductor and leading for a capacitor. So it flips it when you look at the current side. But for the impedance triangle, your capacitance is going to be down. Okay, so that means that these should cancel out the capacitance over there, but we're not gonna go that deep on it. So what we're going to do now is we're just going to go ahead and we're going to test this right here. So we did the and I'm just jumpering these two together, right? This is just a coil. And so we did the check where we said, hey, we know what a capacitor looks like, right? And now we're going to do what a coil looks like. So if we go ahead and we put that in there, okay, so we got 0.36 ohms, right? Well, what happens if I add an iron core to this, right? And this isn't exactly an iron core, but close enough. We're just going to take some lag bolts, stick them in there. Oh my gosh, you can see the meter value is changing, right? And why is that? Because we're changing the inductive properties of that coil, okay? So now the henries of this coil is changing, okay? And so could we figure out what the henries of this coil is? Yeah, we know what the frequency of this is, right? So, and we know what the ohmic value is. So yeah, we could probably get down and figure out the exact henries inside of there. So there's that. Let's do one more, right? What we didn't account for was a little bit of, DC losses from pure resistive connections here, but let's not tear this apart, right? So there's that. Let's do a bigger one, right? What do you expect on this one? You got more turns, right? So at a higher impedance test set, I expect to have, higher frequency test set. At a higher frequency, an inductor looks like a choke. If I have a bigger inductor, it looks like more of a choke. So we had, around 3 ohms before. Sorry, 0.3 ohms. And now we have 1.8. And if I add look how much it jumps down. That's because this thing's a much bigger inductor, okay? So now we're getting quite a bit more on the ohmic value, okay? So there's that. Now let's do one more thing. I have a resistor over here. And so this resistor, well, what do we see, right? Does this still measure resistances like normal? Absolutely, it measures resistances like normal, okay? It's a 10 ohm resistor. I wrote it on here. I'm going to prove that with my meter over here. It's a 10 ohm resistor. We have 10.5 right here. If I just go ahead and I open circuit these, right? We said 10.5. I'm going to take it. I'm going to plug it directly into here. Let's get it off of nanofarads. We don't need that stuff. We're going to go right in here. We're going to plug it in. Got to get it flipped back on because that popped off. Let it scale 10.3, right? So this can measure just fine, but when you have other things in the circuit, it becomes a power triangle. So let's demo that, right? So we know this is 10 ohms. Actually, let's go ahead and set this to 5 because I know my math a little bit. So let's go ahead and get this thing set to around 5 ohms in the middle. 3.2 is fine. This is just a variable resistor, so I could just slide it and change the resistance. So let's, 5, 5.0, 5.1. There's a dot in there. You might not be able to see it very well, but 5.1 ohms. So, and then we're just going to unplug this, and just so you all feel real comfortable about it, I'm going to go ahead and also so you know there's no witchcraft going on here. I'm going to go ahead and I'm going to. Well, my meter just shut off right when I did that. So there we go. And, function check. Always do a function check. 5.1 with the ring. Yep. Put this on here. Boom. Yeah, 4.9. We had 5 on the other one. So perfect. Now let's go ahead and let's make it a real power triangle, right? So now we have a resistor and an inductor, and we're going to change this inductor right here so that way it has a much higher ohmic value. Maybe we can get away with that. So I'm just going to flip this on here, and we're going to check this one, right? 3.1. So if we take 3.1 and we put it in series with this one, right, then you just should expect around 8.1 maybe, or actually it's 3.2. So, you know, we'll just say 8.1, 8.2. So, but is that how it works? No, it's a power triangle. You know, you're going to have resistance 5 ohms this way, 3 ohms of reactive resistance up here. So we're looking at this leg, and so that's actually going to be less than 8. Okay, so we're going to go ahead and get some more jumpers over here, and this may change some of the resistive values, so we'll double check that real quick towards the end. But we need a lot of jumpers, so we're going to go ahead. We're going to jumper from here to coil, I'm sorry, our resistor, and then this is going to go into our test set. This one over here is going to go back to the other side of the resistor. And I'm going to put an extra lead in between all of these jumpers because I want to be able to go to a meter and show you the resistive value of all the leads combined. So I'm going to need an extra lead in there to split. So we go right here and we put that on here and not kill my test leads. And 7.2, huh? So if we add 5 to 3.2, we don't get 8, right? And I'm sure that you guys could go ahead and do the power triangle and figure this out, but this is where it comes from. This is basic AC theory, okay? So now let's go ahead. What's the DC component of all this? Well, this coil is practically a short circuit, okay? But we added quite a bit more copper, so let's go ahead and let's just measure it real quick. We're gonna put this on here, so we should expect a little bit higher than 5 because we added 5 here plus the coil, so 5.6, right? 5.5, 5.6 is your DC circuit, but when you look at your AC circuit, right? I'm just going to jumper these and short them back together. When you look at your AC circuit, because that's an inductor, it's 7.1, 7.2. Okay, so this right here is basic AC electrical theory. DC theory is Ohm's law, pure resistors. Okay, AC theory, you start throwing in all of your stray inductances, capacitances, and everything else. And just as one more little bonus, right, I'm going to take this little capacitor right here, and if I go ahead and I put this in the circuit in parallel with that inductor, it should cancel it out and bring our ohmic value lower. And there it is. So it practically canceled out all of the inductor and brought it down to only the resistor. Isn't that neat? So go ahead and if you want to get out your scratch pad and paper and figure out the math on some of this, have at it. But that's basic AC electrical theory, and I hope that this helps. Thank you.